much. Let's start the opening lectures. So a brief introduction of about Professor Keh-Jian Shou. So he graduated. He got his PhD in 1993 from University of Minnesota, United States. And his research interest is in landslide and related to the climate change, and also about the trendless technology. But today he's going to talk about the landslide and related to the climate change. Professor, yes, sir?
Yes.
The time is yours.
Okay.
Please.
Thank you. Thank you. Thank you for your very gracious introduction. I don't know how many students here and how many professors here. I want to say hello to you all. It is my a great pleasure to deliver this presentation online. The title of my topic, as you can see, is on the spatial landslide hazard with consideration of climate change. As you may know that we have typhoon as one of the natural hazard, and typhoon not only induce flooding but also induce landslide problem, especially after the 1999 NCHU earthquake. We have a big earthquake with the magnitude of 7.6 in Richter scale. So it's a big earthquake. And after the big earthquake, all the geomaterial in the mountain area are highly fractured. So the following 10 to 20 years, we have a serious landslide problem, especially the debris flow, serious debris flow problem at the first 3 to 5 years. So, so what I'm going to share with you is as a landslide problem along a highway in the mountain area, mountainous highway. We try to analyze the rainfall behavior besides the susceptibility of the landslide in this area, especially along the highway, such that the highway authority can prioritize which site they have to handle first, and how they can spend money for the reconstruction in a smarter way. So that's about it. Before I get into the details, I would like to give you some background of the geology in Taiwan area. As you can see, this figure, you can see this figure in many of the textbooks. This is called Ring of Fire. Actually, this orange belt area actually is covered with a lot of volcanoes and also major earthquake also along this orange belt area. So the reason, the real reason behind this is actually this orange belt actually is located at a joint of a plate. So from the plate tectonics, this is, you can understand why there are so many volcanoes and so many big earthquakes along this orange belt. I think the country share the same experience as us, as Taiwan experience. So maybe that I think maybe we can learn from each other, especially for the natural hazard topics. And as you can see, this is a 3D tectonic setting of Taiwan Island. This is Taiwan Island. You can see actually we are located at the joint of two plates. One plate is called the Philippine Sea Plate. Philippine Sea Plate is part of the Pacific Ocean Plate. The other side is we call it Eurasian Plate. So Taiwan is actually at the colliding area of those two plates. So this colliding activity actually generate high mountains in Taiwan Island. For such a small island with about 40,000 kilometers square. It's a very small island, but we have the highest mountain up to about 4,000 above sea level. The reason why we have such a high mountain is due to the tectonic activity. So this tectonic activity not only generate the high-rise, the high mountains, but also cause a lot of earthquake. You can see those red dots actually is the epicenter of the actually hypocenter of the earthquake. And also we have a lot of active fault, longitudinal active fault that can cause serious earthquake damage frequently. Okay, so this is the background of Taiwan geology, but this kind of geologic setting not only induce earthquake but also cause a lot of geologic structures. So our formation is quite various, and also we have highly fractured formations in this island. Okay, this is the background of the geology from the tectonic point of view, and sorry. Okay, this slide shows the major landslide. You can see this actually. I picked up 4 major landslides to show you what we have, what we encountered, especially after the 1999 Chichen earthquake. This one called 9份23 landslide actually is deep slope landslide. It's a large scale landslide. Along the bedding plan, you can see the sliding planes is quite flat. The sliding body actually dam the river. So we have a landslide dam lakes. This could be very dangerous. So this is one of the big, large-scale landslide induced by Chichen earthquake. This is another one, Caolin landslide. This one is also a deep slope landslide, also generate landslide dam lakes. It's very you can see this dam landslide dam is very large, very large. So though actually to treat this kind of large scale landslide, I think the government have to react in a very quick way. So the Water Resource Agency and the Soil Water Conservation Bureau, they dig the temporary channel to reduce the water in the landslide dam reservoir. Okay, and after that, after we solve the problem in the emergency phase, we try to mitigate the problem inside the landslide area, because we still have some residents inside or nearby the landslide area. Some of the government, local government or central government, they try to have kind of policy to buy the land back in order to move the residents from this hazard area. This kind of problem we have and what we have done after the this kind of large-scale landslide problem. This one is we call it this landslide called 九九 peaks. Landslide 九九 means many mountain peaks. You can see a lot of peaks. Actually, this formation in this mountain area is gravelly sedimentary rock. So it's easy to be eroded. So you can see the topography induced by the weathering. However, the cementation of the gravelly soil is gravel formation is not so good. So you can see a lot of erosion gullies, and also you can see the vegetation in this area is not very good. Only have short root vegetation because it's, the weathering rate or the erosion rate is quite high in this area. Although we have more than 2,000 millimeter precipitation every year, enough to have a better long root vegetation. But in this area, you can see not many that kind of vegetation. Induced by the, due to the big earthquake, those shallow landslide will be induced. What I'm trying to say is that this mountain actually is greenish before the earthquake, but after the earthquake, the shallow vegetation actually removed by the earthquake, so it's kind of like a bald head. See, so this is a very special morphology. Site. So a very special one. This one is also we call it shallow landslide. Actually, the mountain is quite high. It's more than 2,000 above sea level. The formation in this area is sandstone or interlayer sandstone, and also some slightly metamorphic rock, also highly fractured due to the activity of tectonics. Also this picture was taken after the Chichi earthquake. You can see a lot of landslide, actually from the peak all the way to the river. So we have a cross island highway about at the middle elevation of this mountain area. So this highway is almost totally destroyed, and we spent more than 10 years couldn't fix it, couldn't reopen it. Even until now, it's not back to the normal condition. The reason for this, you can see the problem is not only along the highway. You can see the problem is from the peak to the river. So it's although it's a shallow landslide, but there's the scale is very large. It's from the mountain peak all the way to the river bed. So it's very difficult to solve the problem. So for this kind of problem, the best way could be the bridge, high-rise bridge, combined with a long tunnel to penetrate this kind of unstable slope. So, but that will cost a lot of money. So we have to have a good planning and also financial planning. Okay, this is I want to share with you some of the major problems we experienced for the past maybe 20 years. And you can see this is another site. It's along the freeway. Also, this is a deep slope. The sliding is along the bedding plan. You can see this picture. Maybe it's too small. Can you see this one? actually this sliding body, this sliding body actually covered the freeway. This freeway was blocked. Fortunately, there's no casualties. But the interesting thing for this landslide is that there's no rain, no rainfall. This sliding is not occurred during the rainy season, so this is very strange. And also during the construction of freeway, we have a lot of cables. We have a reinforcement for the excavated slope, but still this landslide occurred. So if we get back to the reason for this, there are many possible reasons. One of the reasons is erosion of the cables, and another possible reason is the management of the land use, because according to our construction law, we have and the government, highway government or freeway government, they have to buy the land maybe 60 to 100 meter outside of the road, but still you can see for this kind of a long slope, you cannot control the land use outside of the line. So what I'm trying to say is that maybe there are too much irrigation problem, too much irrigation activity outside of the line. And water could get into the sliding plane and also could induce the erosion of the cable. That's the reason why this landslide occurred during the dry season. So this is a potential problem. So after that, we have kind of a monitoring for those cables along the important freeway. We have a kind of monitoring system after that. Also, we have a strict reinforcement of the land use outside of the line as well. And this is another case. Actually, I adopted this from the previous slide. You can see, as I said, that the landslide is, although it's a shallow landslide, but it is from the mountain peak all the way to the river. I'm trying to explain that to you. You can see this is actually a freeway route at the middle of the slope, middle height of the slope. You can see some of the we call it semi tunnel actually is isolated because the road nearby actually is the foundation actually all slided down to the river. So this road is almost impossible to reconstruct it. So this, you can see, this is the real problem. This is also another type of landslide as a debris flow problem. You can see this is debris flow is also caused by the active fault activity, because this active fault is a thrust fault. So cause the elevation of the ground, but due to the regionalization of the river, so the incision rate is very high. So you can see a lot of landslide in the upstreams. So a lot of debris in the riverbed in the upstream. During the rainy season, we have debris flow. Serious debris flow. So this debris flow actually is a kind of a natural, natural behavior. You can see this. I am trying to use this figure, this picture to show you what I'm trying, what we have. Actually, you can see this is a tree, pine tree. Actually, the pine tree grow up on top of the debris flow. So which means the debris flow happened maybe more than 100 or 1,000 years. So this is a natural behavior of the motherland. If we can see the potential hazard or susceptibility of the debris flow, we better not choose this site as a residential area. If we look at the residents in this area, this is a mountain area. We have some Aboriginal village in this area as well, because their ancestors lived in this area maybe more than 1,000 to 2,000 years. So you can see their resident village actually is on the upper riverbed area on the other side, not in this dangerous area. So they learn this from their the history. So this is so some of the landslide or the debris flow is a natural behavior. It's not induced by if we know where those hazards are located, we can avoid it by not living this kind of area to avoid the hazard, avoid the risk. Okay. Now I'm going to move back to the climate change. You can see that this is a variation. This is a rainfall record in Taiwan area. You can see we have this is an annual precipitation. It's about normal, but the rainy days, the number of the rainy days is reduced, which also means that the daily rainfall increased. So the total annual rainfall is not much different, but the daily rainfall increased. So which also means that rainfall is more concentrated. That caused the problem even worse for the past few years. So I think we experience this kind of problem not only in Taiwan, but probably in your country as well. It's a global problem. I think also we have a water shortage problem. I attended one of the Water Resource Agency conference. They have a water shortage in their reservoir as well, because the rainfall is more concentrated and also might not fall down at the upstream area. So they have a problem for the water supply, especially for the farming irrigation as well. Okay, this is a problem. Okay, so that's this is what I want to share with you, what we have, what we experience. Now I'm going to move back to my topic. Actually, it's one of my paper published in engineering geology. If you like, if you are interested in this topic, I can share with you the link after the presentation. The presentation I'm going to deliver. As you can see, we have 4 parts. The first part is about the introduction of the problem of this topic, and also I'm going to talk about the rainfall analysis, landslide analysis, followed by a brief conclusion. Okay, so so as I mentioned in the second slide, we encountered a big earthquake, the Chichen earthquake in 1999, and so the formation are highly fractured. We also encountered 2 very big typhoon, have about 1,000 to 2,000 millimeter rainfall in 24 to 48 hours. So it's a very heavy rain induced by those 2 typhoon, one in 2004, one in 2009. Not only caused a flooding problem, but also caused a serious landslide problem. This is also the background of the landslide as well. And in this study, we collect rainfall data. We try to use the rainfall model to analyze the data. We try to use the model to predict the rainfall in different recurrence period. And also we try to use the atmospheric general circulation model. Actually, this model is generated by the expert in weather forecast. So they generate and modify the model, and we obtain the rainfall predicted by their model. But their model have a resolution of 1 kilometer pixel. So we have to use the downscale technology to get a better resolution rainfall distribution based on their model. Okay, and for the landslide analysis, we try to use 2 different methods to obtain the landslide susceptibility by consideration of the rainfall in different occurrence period. So the model of for the landslide analysis, we adopted 2 different methods. One is the logistic regression, and the other one is supporting vector machines. Those are the quite popular method for landslide analysis in regional or catchment scale. So it's although we have to use some procedures to verify or calibrate the model before we can do the prediction. Okay. This area is actually the upstream of the we call it Wuxi River in central Taiwan. Maybe this is too small. It's, the red area actually is this study area. You can see in this area we have different kind of formations, different rock formations. Different color represent different formations. In this area, metamorphic rocks or slightly metamorphic rocks. But there's a mountain highway in the middle of this study area. Is in the slate formation or slate formation. Yeah, slate formation. We call it Lushan slate formation. And you can see they are 2 free lines, one in red and the other 2 in black. The black lines are the fault lines. Fault lines. The formation was broken by the fault. Okay? The fault actually thrust fault. So the east side of the formation were uplifted by this active faulting movement. And the red line actually is the fault axis of the east side of the formation because of the squeezing. So the formation is kind of bended. So this is a we call it anticline, which means the bend is the concave is in the lower part, is bended to the upper direction. So although this is the fold axis, okay, FOLD, the banded formation. Okay? So this is the location of the largest curvature of the fold. Okay, so this is a geology background, including the formation and those structures. And as I said, that this mountain freeway is somewhere around here, beside the major fold and the fold line, the black one and red one. And they are about 5 to 10 large-scale landslide along this mountain highway. They frequently cause a problem and stop the operation of the mountain highway. So the residents in those small villages is a problem to have their transportation. But the economy activity in this area is, I mean, the transportation is important for the economy activity in this area, because this area is famous for their mountain vegetable, and also famous for their mountain teas. So it's a very high price farming product in this mountain area. So the transportation is very important in this area. So that's why we try to figure out what is the distribution of the hazard, and which one is more dangerous, which one should be treated first. So this is the background of this study. Okay. So the title, Spatial Risk Analysis, means we try to analyze the risk in the risk distribution in this area. Okay. Let's move on to the rainfall analysis. As I said, we collect the data, the rainfall data from the Central Weather Bureau. Before we do the rainfall analysis, we do some verification, remove the unreliable data. Before we do the analysis, we use a lot of model, popular rainfall frequency analysis models. You can easily find those models in the SPSS package. Okay. We try to find the most suitable model for the data we have in this area. We found that maybe the normal distribution model and the hazard model is better, compared with comparatively better in fitting. Okay, so we use the regression model to do the prediction with different recurrence period. I would like to point out that the data we collect actually is down to the hourly rainfall, so we can predict the rainfall intensity on the hourly basis. Okay. So based on the model, that we train the model, and then we can predict the 24, 48, and 72 hours accumulated rainfall with different return period. Okay. So this is the rainfall frequency analysis based on the data for the past 10 or 20 years in different weathering station in this mountain area. We have maybe 10 to 10, more than 10 rainfall station in this area. Okay, this is the results of the rainfall frequency analysis. This is a 20-year return period, 100-year return period. Normal distribution. Based on the normal distribution model, based on the hazard model. So we can see that the 100-year return period rainfall is much higher than the 20-year return period prediction, and also you can see that for the 20-year return period, the difference between the normal distribution and the hazard model is quite similar, but for the 100 return period with 72-hour accumulated rainfall, the hazard model is more conservative, more higher. I mean, you can see about maybe 20% more. Okay. Okay. After we generate the established model, we can estimate the rainfall in different rainfall stations, because we analyze the data based on the data in that rainfall station. In order to get the rainfall distribution, predicted rainfall distribution, we use the kriging, this kind of geostatics statics function. Also, you can find this in different packages, or even in maybe some of the software, or you can use software. General graphic software, you can do this. We use the kriging to get the distribution of the rainfall. This is based on the rainfall frequency analysis. Okay, this is from the normal distribution model. This is from the hazard model. And for the second method, the climate change model, as I mentioned, we used we call it the weather. Actually, we get the model from there's a platform called the Taiwan Climate Change Projection Information Platform Project. It's one of the national research center. They did this kind of establishment, and we get the data from their prediction. You can see the resolution is down to about 5 kilometer resolution. They can predict the near future rainfall, and also far future distribution prediction, rainfall distribution prediction. But their model is based on the weather model. So the weather model actually for the extreme rainfall in Taiwan area is due to the typhoon. So those model actually also depends on the the routes of the typhoon. So when we use this kind of prediction, we must be careful about the suitability of the prediction, because sometimes your study area, it depends on, some of the typhoon route impact the specific study area more heavily than the other area. So when we use this model, based on our experience, we found that we have to consider the typhoon route as well. Okay, and also within their model, they also have a different, we call it, you can see, I think they have a different detailed weather model. They have different assumptions. So also they update those models frequently. So, however, this model is more typhoon based. It's not the pure statistics. So you can see from this slide, you can see they classify the typhoon route in typhoon area to maybe 10 different routes, and you can see different route can have a different prediction, and they arrange a list. You can see the route 1 and route 2 can create the most precipitation according to their weather model. But you can see not necessarily, you can see the route 1 generate the high risk rainfall for near future, but for the far future, typhoon route 1 is not so serious compared with the typhoon route 2. So this is quite interesting. Okay. But for our study area, maybe route 2 and route 3 is major one, because our study area is somewhere around here. So route 1 is not so serious for us. So that's why what I mentioned, that we have to consider route as well, not just use their model directly. Okay, this is the results. After we get the downscale data, we also use the kriging to create the data at the sampling point of their prediction. And these are the predicted rainfall distribution based on the climate change model for the near future and the far future. Okay. So now let's move on to the landslide analysis. What we try to analyze is the landslide, special landslide hazard or special landslide susceptibility. Those model we adopted, that is the logistic regression and support vector machine, actually are all the statistics one. So we have to decide which causative factor we are going to use. So here, I don't have enough time to go into the details, but I'm trying to say is that the rainfall factor we adopt actually is a combination of the rainfall intensity and the cumulative rainfall, because for our rainfall-induced landslide is mainly induced by typhoon. For typhoon, the rainfall behavior, actually those two factors are interconnected, interrelated, interdependent. So we cannot use them as the two independent causative factor. So we introduce one factor we call the landslide rainfall index. We spot the landslides, the rainfall at the landslide site according to the landslide inventory, so we can see this distribution of the rainfall at the landslide site. Then we can find the upper bound, lower bound. We use the formula to define the index. So the index is actually normalized between 0 and 1. So we use this index to see how strong the rainfall can influence the landslide susceptibility. This is one of the factor. So each factor in this those are the landslide rainfall index for different based on different predicted rainfalls, such as the rainfall frequency analysis and also the weather model. Okay, so from this logistic regression method, you can see we adopted 9 causative factors based on training. So there are 9 causative factors. So we collect the data to generate normalized data layers before we do the logistic regression. This is the result. Also, we use the ROC curve using the AUC value to verify how good the model was generated. Okay, the left-hand side actually is logistic regression results based on the 2004 Minduri typhoon. So it's reasonably good, this is for the prediction. You can see we use the trained model, logistic regression model, to do the prediction. Actually, we changed the rainfall to the prediction rainfall to do the prediction. This is a special distribution of the landslide susceptibility in the study area. And also, we use as I said, we use the Sipil vector machine method. Also, we use the same 9 causative factor to do the analysis. Those are the results. Actually, the weight, some kind of weighting factor. Okay. Also, we use the landslide inventory of 2004 Minduri to do the training. You can see the AUC value is better this is the result. Also, based on the predicted rainfall, we can do the prediction of the landslide susceptibility in the study area. So this is a kind of a summary and the comparison. I think I almost run out of time. I'm going to skip this part. And this is the key issue we are trying to tackle. As I said, that we have a major landslide along this mountain highway. We try to see which side is more dangerous than the other. So after we obtain the susceptibility distribution, we can find the susceptibility at the specific point. So as those landslides actually have a GPS location, we can see the landslide susceptibility based on the predicted distribution. So those are the susceptibility based on the predicted distribution. So then now we can see which one is more dangerous than the others. Those are the values. Those are the rankings. So now we know the ranking, which one is better, is more dangerous. Then we know which site is should be treated first, or should spend more money for the reconstruction first. Okay, so this is the whole idea of this study. Also, we try to, because this, the one we have, I mean, I show you in the previous slide is based on the statistic based analysis. This slide shows the study or analysis based on the limited equilibrium analysis, because we have also have some drilling data, so we can do the limited equilibrium analysis. You can see the ranking of the major landslide by limited equilibrium analysis with a different groundwater level condition. You can see also you get the ranking. So we can have a kind of a recheck or actually we can have a comparing. Because if we use only one method, maybe this people might question you about so many assumptions. So we can. What I'm trying to say, if those two methods, limit equilibrium analysis result ranking, and this statistical approach ranking, all focus on the same side is more dangerous. It's also support the results. Okay, support your decision. Okay. Okay, this is the picture that I think this after 2017 with a limited drainage or rehabilitation. So you can see this is still not fully covered because we gradually treat the construction or treat the landslide problem from the southern part to the north. So not only we have to consider the ranking, but also we have to consider the accessibility. So that's another issue. Okay, I think that's about it. I'm going to summarize a little bit. We try to use the rainfall analysis to do the prediction of the rainfall distribution in different recurring term period of time, and also we established the landslide model to analyze the landslide susceptibility, and we integrate the rainfall analysis and the landslide analysis to understand the special landslide risk, such that we can assess the landslide problem along this mountain highway. Okay, that's about it. Thank you for your attention. Thank you.
Thank you, Prof, for
Question?
very nice presentations. I think we still, if you have time for question and answer for a few questions, Professor.
Yeah, sure. No problem.
Okay, is there any questions? If you are having difficulty in saying it in English, you can say it in Bahasa, and I will translate it for you, and I will say your question to Professor. Please, is there any questions, students, or anyone?
Ada, Pak.
Yes, please. Say your name.
My name is Dian Karisma, Professor.
Yes.
Okay, please.
Okay.
So she is a new student.
Yes. This is a very interesting topic for me. Forgive my English if I can speak well. Professor, I want to know, in a year, how many times typhoon hit Taiwan?
It's I think maybe in average we have 3 to 5 typhoons, but maybe only 1 to 2 make a touchdown in the center of the typhoon, touchdown on the ground. But for the past maybe 3 years, almost no touchdown. It's kind of, as you can see from the news, most of the typhoon, they change their route to Japan. You can see the news. Very, very strange thing. So that also caused the water shortage in Taiwan, because although the typhoon caused a problem, caused the natural hazard, but also typhoon also create a rainfall. We need the rainfall as well. So our water reservoir have obtained the water from the typhoon as well. So what I'm trying to say is that the climate change is undergoing. So I don't know whether or not the typhoon will come back or not. But we predict that maybe, as you can see from the very beginning, maybe if we have a typhoon in the near future, maybe it might be more serious than before. The total amount must be the same in nature, but we are short of the amount for such a long time. So if we have a next one in the near future, it might be more serious than before. So we have to record it. We have a preparedness. We have to prepare the worst situation. So this is what we try to do now. We try to prepare not only the construction but also the management. Government have to organize the different group to prepare for the serious natural hazard such as the typhoon, flooding, and also earthquake.
Okay.
So is the question now?
Yeah. I just want to ask what the government make before the prediction of typhoon hit Taiwan. But as your presentation in 2 or 3 slides, I see the freeway. You said that it's a strange case, right? No rainfall in a dry season. It's very strange. Maybe it's very sudden.
Yes,
what
very
I want
sudden.
to ask, what I wanted to ask is, what kind of emergency treatment that the government made for the case like this? It's a freeway. Are you blocking the way, or some kind of the treatment? I want to know, Professor.
Yeah, and as I said, this is a freeway. It's a very important freeway. So actually, this is an excavated slope, which means the original topography is like this, the green one. Okay, but because they want to construct this freeway, they excavate the slope, and they install the cables to reinforce the slope. After the sliding, the freeway was blocked. So first of all, they want to they take a lot of evidence before they remove the sliding block. So I remember that they finished the cleaning maybe in, because the mass is quite large, maybe around 10 to 14 days. Remove all the unstable sliding blocks, the rock mass, and then they try to fix the problem. I don't remember how much time they open this freeway back to the public. Maybe in 1 year. Maybe in one. I don't know the exact number, but maybe in 1 year, because they have to reinforce the slope, stabilize the slope again, and also they have to check the because you can see this this freeway is a kind of a high rise because there are some bridge, so they have to reconstruct the structure as well. So it's kind of complicated. Since there's no casualty, so it's not too bad. It's a lucky thing for this instance, because if there's a casualty, maybe car or casualty covered by the sliding bike, that will be not only the engineering problem but also political or social problem. That will be much more serious. Yeah, some of the I think some of the natural hazard like earthquake. I think engineering might not be the most urgent emergency task they have to handle. They have to handle the casualty first in Taiwan. I don't know whether it's also the same thing in your country or not. We have to make sure that all the bodies or the casualties are properly handled. That's the first thing. And second thing is to stabilize the problem, solve the problem, and reconstruct and make it back to normal and open to the public again.
Okay, thank you, Professor.
Okay.
Thank you, Dian. We have also another student who want to ask.
Yeah.
Harwinder Denta, please.
Okay, thank you
Mr.
for
Harwinder.
that.
Yes.
I will introduce my name. My name is Harwinder Denta, Professor. I want to ask about the factor that you use in the analysis. There's, I think, 9 or 8 factor, I think. I forget.
For F1 to F9, the weighting factor.
F1 to F9.
Yeah.
Yeah.
F1, F9 is the landslide rainfall. Yeah, this one.
Yeah. I want to ask about if there's a structure that prevent the landslide, like corrugated sheet pile or something like that, to prevent the landslide. Is there a factor about that? That's the first question.
No, actually, the study, the analysis is in the, we call it regional scale or the catchment scale. So it's analysis since in the regional scale, we use the pixel of maybe 10 meter by 10 meter or 5 meter by 5 meter. That's about the resolution we have. So it's not the site-based analysis, it's statistical study. So we don't consider the, yeah. Okay?
Thank
We
you.
don't consider the resource.
Okay, the second question is, after we simulate the condition, we have index from 0 to 1 for the susceptibility
Yes.
susceptibility from 0 to 1, and
Yes.
after the analysis, we give it to the government to make some change in that area. My question is, after we make change in that area, can we analyze again to know the index, the susceptibility index is decreasing. So
Yes, yes, yes. You're right. Yeah, you're right. For this, susceptibility analysis model, you can see from those causative factor. There's only you can see some topography factor, some geologic factor, and the rainfall factor. So as I said, it's only for the regional scale. So you are right. This you cannot consider the mitigation or the influence of mitigation or the other factor. However, it is possible you include more causative factor, including those influence, but still it's not so. I can imagine it will not be so significant because it is in a regional scale, catchment scale. It's a very large scale, so very large area. So if you spend the money, I think the impact will be very insignificant from this kind of scale. But if you study the problem in a local scale means that your area is smaller, maybe the mitigation influence will be more significant, and then you can add more factor in this model, this kind of model, to include this influence of the mitigation or treatment. Okay, so
okay.
Yeah, this is a kind of a scale problem. Yeah, but the method that could be used in the local scale analysis.
Okay, thank you, Bob.
Thank you. I think I will give one more chance for a questions before we finish because we have. Yes, is there any other question?
Yeah, Pak Yusa.
Yes.
Mardi, yeah. Please,
Yeah,
yes,
thank
please.
you, Pak Yusa. Hello, Prof. What do you call Albert? Prof. Albert or Albert Shou?
Yes, yes.
Prof. Albert, yeah. My name Muhardi. I'm lecturer in geotechnical engineering in Riau University. I'm colleague Muhammad Yusa, Pak Muhammad Yusa. Okay. Very interesting about your presentation, how to predict the landslide. Yeah, how to predict landslide. There are one or two questions for me. Maybe is it out of the topic? I want to ask you about how do you manage landslide in Taiwan? I don't look at in your presentation how to manage, how do you stabilize landslide in Taiwan?
Okay. I'm trying to use this case to show you. For this kind of landslide, we should have a kind of a investigation first to understand the behavior and the mechanism of the problem first before we do the treatment. The treatment could be remove the unstable material on the slope, and also some drainage treatment, including the horizontal drainage pipe, and also vertical shaft to collect the water and pump the water to other places. And also we, in some large-scale landslide, we also use the drainage gallery, the horizontal tunnel, small-sized tunnel to collect the water. We call it gallery, horizontal gallery to collect water. So that's from the groundwater point of view, because in this kind of a landslide, the groundwater could be the major issue. Okay, together with the treatment, we also do some monitoring, including the groundwater level monitoring, and also we install some kind of a clinometer. We can measure the deformation in the borehole to see where the sliding plane is located and how much the displacement, the sliding displacement occurred before or after the big rainfall event. So what I'm trying to say is that some of the monitoring could last more than 5 to 10 years, especially for the large scale landslide. Okay, and on the construction point of view, we reconstruct the road in a like a primitive way, in a lower level in the very beginning, because we have to finish the treatment before we do the final construction of the road. So that's about the whole process briefly, in brief. I'm wondering, I answer your question or not. Is that what you want? Oh, by the way, we also do some we call it protection or reinforcement as well. We also install the sheet pile or shaft pile, and also some cables to reinforce the surface. Yeah.
Okay. Could you show the more photo of the stabilization in the other area? Maybe you can show the other photo. How do you manage?
You mean this one or this one?
I mean about the how the photo of the landslide stabilization. Maybe you can put the pile, you can put the right and the other.
Yeah, for this one, you talking about this one or the one in the very beginning?
I think okay.
The other, if you have the other photo about the landslide stabilization, how?
You want me to show you
More
pictures?
photograph. Yeah,
Oh,
more picture.
yeah, but
if you have.
yeah, not in my. It's not. I didn't prepare that. So sorry about that.
If you don't have, no problem. Okay, yeah. Okay, okay.
For example, along this freeway, you can see if we want to reconstruct this highway, we might have to reconstruct this semi tunnel. I'm not sure. I can enlarge that or not.
Okay. The next question.
Okay, last questions.
Yeah. How do one
See, this one.
How do you compare your prediction with the real condition? Is this close the prediction of your condition?
Yes, as I said that we use this actually through the training of the model. Actually, it's a kind of a confirmation of
machine learning.
Yeah, and also for this specific site, we double check what our prediction. It's not in this presentation. We found that our prediction quite reasonable. Not maybe not 100% correct, but maybe 80% correct, based on what we predict.
Did you file now, eh? Okay.
Yeah, yeah.
Yeah.
Okay, I think is that answer your question, Pak Mardi?
Yeah. Thank you, Prof.
Okay, my pleasure.
Okay. If thank you very much, Professor. If you want, if you don't mind, is it okay for? I mean, if there is any student or our lecturer here, if you who wants to make contact with you or email?
Yeah, sure. You can see. I want to go back to the original scale, but I couldn't.
Nanti ya. Nampak aja kan. Ini ada.
I do have one. You can see in the one last page. Did you see this email? Can you see the email?
Well, no.
No? What about here?
I think you
I'm
need to share
Wait.
the file.
Oh, yeah.
Taiwan. Ya.
Can you see it now? This is the email.
Okay. So that's thank you for willingness to share your email. So hopefully we can pursue or continue our cooperation later on in the. So I think before we end, can we take pictures? You can please show up your face. So Faridwan, can you help so we can take pictures? Faridwan,
Yes.
can you take the whole picture of us, all of us?
Okay. Before we start, would you please, Prof, to unshare your presentation file so we can see all the pictures of the participants?
Can you see now? Can you see now?
Yeah. Can you? Yes. Can you please stop the share screen first, and then so we can take pictures?
Okay. You want me
if
to?
Yes, stop the screen and so we can take pictures.
Okay.
All of us. Okay, thank you. Okay, please show your video, all of you. And Pak Kadafi, Pak Mauli, Pak Pandi, please show off your face. Pak Mauli, Pak Kadafi, Pak Mauli, Pak Eka, Bu Yunita. Okay, it doesn't matter that maybe they are away. So, okay. Pak Ridwan, have you taken some pictures? Ready? Pak Ridwan? Okay, I think I will do it.
Okay, done.
Okay, thank you very much, Professor, for your very nice presentations. Hopefully, our cooperation will be continue in the next and in the futures. And if you don't mind, maybe you can share your presentation. Maybe just email me, and then I will share it with the students. If you don't mind, of course.
Okay.
Is it okay?
Yeah, I will.
Okay.
No problem.
Okay. Okay, I think thank you much for your all participation for today's talk. Hopefully we can see you again in the futures. Thank you again for Professor Albert Keh-Jian Shou. I think that's all. So yeah, bye all.
Okay, thank
See you
you.
next time.
Take care. Bye.
Thank you. Thank you, Professor. Thank you.
Thank you, Professor. Bye bye.
Now for student, okay. You still have lectures. I think I don't know whether you have still lecture with other lecturers. Yeah.
Yeah,
Yes,
tell you what, before you finish that, tell you what,
Yes.
we are, because as you may know, that I am a former president of Chinese Taipei Geotechnical Society. We are going to have a webinar, a
Okay.
series of webinar. I will let you know. Maybe one by the end of this year and two more early next year. I will give you the schedule, and you could notify your colleagues or your students if they can, if they have time, they can join the webinar. Okay, online. Okay, it's for free. Okay.
Okay. Thank you very much, Prof.
I will give you the information.
Very appreciate very much. So anyone who want to pursue your study, maybe next sometime in the Taiwan, maybe one option
Welcome.
is to
Welcome. Yeah, welcome.
you can contact Professor Albert Shou. Okay, bye.
Okay, bye. Bye.
Bye. Thank you. Thank you. Mahasiswa baru tetap dapat mengikuti perkuliahan, apalagi sebenarnya waktu kita dalam masa COVID-19 ini, waktu kita sebenarnya relatif banyak dan besar kemungkinan kita perkuliahan kita memang akan kita lakukan secara online. Jadi tidak ada alasan sebenarnya untuk tidak mengikuti perkuliahan. Ya. Sedikit informasi sebenarnya saat ini program S2 memang dengan Taiwan belum ada formal, akan saya coba jajakin dengan NCHU. Tapi yang sudah ada adalah program double degree dengan University of Yamaguchi, Jepang. Itu 1 tahun di sini, 1 tahun di sana. Jadi untuk tahun depan atau beberapa tahun depan, saya cuma buka informasi saja dulu karena masih tahun pertama ini kalian. Bapak-bapak ibu sekalian, jadi ada kesempatan untuk memperoleh double degree dengan Jepang, yaitu jadi tetap bayar SPP di UNRI, kemudian 1 tahun di Jepang itu cuma menambah kurang lebih 5 mata kuliah, free SPP, cuma ya untuk biaya hidup saja nanti yang kalian yang harus dipersiapkan. Itu nanti double degree ya. Jadi itu kalau ya yang untuk informasi saat ini, siapa tahu ada yang tertarik ya. Mudah-mudahan kita akan coba juga dengan Taiwan sehingga terbuka opsi lain selain dengan Jepang, karena Taiwan secara Jepang itu juga mungkin dari segi biaya hidup mungkin lebih murah di Taiwan ya, dan setahu saya sih sebulan 3 jutaan masih oke ya, 3,5 juta ya di Taiwan itu biaya hidup. Jepang sekitar 5 juta kalau biaya hidup itu sudah sekitar 5 jutaan ya. Jadi sudah ada yang mahasiswa kita yang sudah ikut program double degree yang ke Jepang dan sudah lulus ya. Jadi itu sebagai bukti nyata bahwa programnya sudah pernah berjalan. Baik, saya rasa itu. Ada lagi Ci, kira-kira yang mau disampaikan Ci kalau dari segi administrasi Ci?
Administrasi kalau pengisian KRS sudah semua Bapak.
Baik. Nanti absen gimana ya? Nanti dengan masing-masing dosen berarti ya?
Iya, masing-masing dosen.
Baik, Bapak Ibu, mungkin ada pertanyaan, silakan. Sebelum kita tutup, terutama untuk mahasiswa baru, ada pertanyaan? Ini yang mahasiswa baru, kira-kira ini yang kerja, yang sudah kerja, yang lagi kerja, berapa orang? Wah, ini ada itu ya Pak Andri ya. Pak Andri di mana Pak Andri? Kerja di mana ini? Halo? Suaranya nggak ada Pak Andri? Oke, saya rasa itu dulu. Mungkin saya nggak tahu, mungkin ada kuliah yang lain. Saya rasa untuk kuliah perdana kita cukupkan sampai di sini. Lebih dan kurang saya mohon maaf. Terima kasih atas segala perhatian semuanya. Saya tutup dengan ucapan alhamdulillahirobbilalamin. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Terima kasih Pak Ridwan.